Okay, so I'll chair the session, and it's my pleasure to introduce you to Bruno Dutertre. He's a senior principal applied scientist at Amazon Web Services, where he works on SMT solvers and applications. He has more than 15 years of experience in research and development of satisfiability modular theory solvers in applications to model checking. He was also the main developer of the YSIS2 SMT solver. So it's a pleasure to have you here, Bruno. I'm particularly excited because, I'm a total model checking kind of guy, but I am very old-fashioned. My stuff is on BDDs, so I'm quite anxious to hear what you have to say. Thank you.
Thank you. I want to thank the organizer for the opportunity to talk today. And I will cover basics of SMT and a little bit of SAT. If you have any questions, I'm not exactly sure how that would work, but feel free to interrupt and I will try to do my best to answer. Okay, so just to give you the context, I will start by describing quickly what's SMT. So the problem of SMT is to take a formula like that one here and decide whether this formula is satisfiable or not. And what that means is you see the variables in the formula, I, j, the function f, and the array r, a. Can we find values for these different variables that make the formula true? In this particular example, by doing a little bit of arithmetic and array reasoning, we can quickly figure out that the answer is no. So we can see here. So for example, I can do arithmetic on I plus 2 equals j, do some substitution, and that gives me this. Using the array theory, I can say that if you update array A by writing 3 at position I, and then you read back position I, you will get 3. And then at this point, we have a contradiction. So we know that this formula is not satisfiable. Here's another example that's satisfied. Sorry, is there a question?
No, I don't think so.
Okay. So here is another variant of the examples, and this one is satisfiable, and a possible model is shown here. So there's many possible solutions, but this one would work. You replace I by 0, j by 2. You set the array A to everything 0, and then you define your function f this way, for example. And you can just show by substitution in this case that everything works fine. Okay. So that's what SMT is all about, and we are trying to write algorithms and tools to solve this type of problems. So in general, an SMT solver is a function that is a tool that's going to check satisfiability of this type of formulas I described before. Typically, SMT solvers are specialized for some theories, typically decidable theories, but not always. And in most cases, they don't have quantifiers, but some SMT solvers also support quantifiers. So it can be very broad in what they can do. The basic question that people want to know is this formula satisfiable? And in most cases, if the formula is satisfiable, we want a solution. We want a model that shows why the formula is satisfiable. And if the formula is not satisfiable, then we want the answer, but we can also have some solvers will provide extra information like a proof that the formula is not satisfiable, a subset of the assertions that are sufficient, what we call the unsat core, a subset of the assertions that's sufficient to reach unsatisfiability, and many more features are usually implemented, like incremental solving. Other tools provide things like interpolants that can be useful in model checking and many other applications. So it's just a big tool that manipulates logical formula, solves them, and provides results. Here's a list of all the solvers I know about. I think I may have forgotten a few. There are quite a lot. The general purpose solvers are quite famous, like Z3. I'm sure many people have heard of Z3. CC5 is also very famous. You also have much more specialized tools. A lot of tools are specialized on bit vectors. Some do strings and some do nonlinear arithmetic. And I put the link to most of these tools. Most of them are open source. I think the only one that's not open source is MathSap. Okay, so how do these solvers work under the hood? Most of them use an approach called CDCL, modulo T, which is the main approach people have developed for solving SMT problems. It started in the early 2000s, and it's a combination of what I draw on the right here, sorry, a theory solver, which is a specialized decision procedure for the theories you care about, and a SAT solver, which were being developed at the time. So early 2000s, so was the time when SHAF was becoming famous. The beginnings of Minisat also started at that time. So we had emerging very good SAT solver that made a big difference. So I will today, to introduce the concepts, I will focus on a simple theory called quantifier-free uninterpreted functions. So this is the SMT-lib jargon that we use, QF, UF. SMT-lib is the standard used by SMT solver for notation and also for benchmarks and various other things. So essentially, it's first-order logic with equality. So I just describe what it means here. You have function symbols, constants, equality between terms, and quantifier-free formulas. So it's a very simple first-order logic without quantifiers and without uninterpreted predicates. So it's kind of very basic, but it already covers most of the things you have to do to implement an SMT solver. And here is the semantics. Again, it's totally classic. The models for this theory is a non-empty set, and an interpretation that gives you the interpretation for every symbol in your signature. So you need to map constant to an element of the domain, and you map functions to the right type of functions between elements in the domain. And then once you do that, everything else is standard first-order logic. You can interpret terms in the obvious way, and you can interpret formulas in a standard way also. And then the question of satisfiability is, does there exist a model that satisfies my formula? So is this clear? No questions on this? Okay, so let's move along. Okay, so as I said before, there were two big components in an SMT solver: the SAT solver, which is using the CDCL approach, which means conflict-driven close learning. So let me go through that first, and then I will describe theory solvers, the part that handles theories. So here is a quick refresher on what the SAT solvers do. They take a formula in conjunctive normal form, which is shown on the left here. So you have Boolean variables, literals that are either Boolean variables or negation of Boolean variables, clauses that are disjunctions of literals, and the formula itself is a conjunction of clauses. So I usually write it without the and sign, but the idea here is if you want to satisfy this formula, you have to satisfy all the clauses. In the case of Boolean, the notion of model is essentially a Boolean assignment that's going to map a value between true or false to every variable. And then the question, as before, is there an assignment that's going to make my formula true? Okay. Okay, so this is a very well-known problem. It's the original NP-complete problem. And there's been a lot of work on this. And CDCL is actually an extension of a very old idea that was started in the 1960s. That's called DPLL, which is essentially a backtrack search method, combination of backtrack search and another technique called resolution. And the DPLL, especially the version described in the 1961 paper, is essentially building a search tree. So you start with a partial assignment, sigma, and then you pick a variable, you assign it a value, and then you do what's called Boolean propagation, which is compute consequences of this assignment. If you get to a falsified clause, if your current assignment makes one clause false, then you know it's not correct. You have to backtrack and try something else. And that's essentially the algorithm. And then you finish when either you reach a complete branch in your search tree, so you have a full assignment, or you return unsat when you have explored the whole tree. So that was essentially how CDCL started. So let me discuss what I mentioned before, just now, the idea of computing consequences of an assignment. This is called unit propagation. And this is what it means. We start with a partial assignment sigma that maps values to some of the variables, and bottoms mean no assignment for some other variable. And then if we look at a clause that contains these literals, then we can see that there are three different cases. The clause can be true. This happens if one of these literals showing up in the clause has value 1. The clause can be false, which happens when they are all false. And in otherwise, we don't know the value of the clause. It doesn't have a value yet, which means that and this happens if some of literals are false and some of the literals have no value. And unit propagation is the idea that if there is only one literal that's left and all the other literals are false, then the only way to extend your current assignment sigma is by making the last literal true. So in notation, you can look at it this way. So you have a clause of the form C prime or X. It's not fully assigned, but C prime is false. Then the only way to make C prime or X true is to extend sigma by setting X to 1. And there is the symmetric case for negation here. So this is one of the most important principles in SAT solving, and the core of SAT solving. One of the main reasons why SAT solving is successful is the efficiency of unit propagation, or to do unit propagation efficiently. Another important part of CDCL, which is new in CDCL and was not in the DPLL family of techniques, is conflict analysis, which is the way CDCL uses for backtracking. So a conflict happens when your assignment makes one of the clauses false, which means that all the literals are false in that clause. At that point, you have to backtrack and update. And what CDCL does is backtrack by learning a new clause that is derived from the conflict clause C here. And it is also computed by looking at previous unit propagation steps and reversing this unit propagation step until you find a clause D that has good properties, and you use this clause D to backtrack. And one of the impacts of computing the clause D, so informally, you can think of D as the reason why the clause C was falsified. It's kind of a summary of why C was satisfied, and it will rule out, it will stop you from redoing the same mistake again, doing an assignment that's similar to sigma and would lead exactly to the same clause. So it's a good way of pruning the search. And it has some other properties that are used by the SAT solvers. So let's look into more details on how that works. So I didn't try to...
Can we ask questions?
Yeah, sure. Go ahead.
Yeah, but adding these conflict clauses actually increases the number of clauses. So
Yeah.
Doesn't that make it harder to search for all the clauses?
So there are two answers to that. First, it increased the number of clauses, but not the number of variables. Number of variables is more significant than the number of clauses in terms of size of the problem and complexity. Then there are very good data structures that allow you to keep doing very efficient Boolean propagation, even though you may have many more clauses than you started from. And another thing that SAT solvers do is they do garbage collection. So from time to time, they are going to delete some of these learned clauses. They try to use different heuristics to figure out which clauses look useful, and then they delete the clauses that are not useful. So that addresses your problem, and it's also very useful in practice. It stops you from running out of memory. From time to time, you just need to delete some clauses that don't seem to be that useful anymore. So you lose, in some sense, by doing that, you lose the second point here. You may redo the same mistake, and then possibly you may even learn the same clauses again. So you learn a clause, you do garbage collection, you delete it. Later on, you may have to learn it again. But that's a good trade-off.
Thank you.
Okay, so the way it works is internally a SAT solver is going to maintain an assignment stack, which is assignment of variable to values, or another way of looking at it is a stack of literals that are true, and it's organized by decision level. A decision level is essentially starts, so except for the base level 0 here, every time you do a branch in your search tree, you make a decision. So you pick a variable and you decide to make it true or false. That's called a decision. And that starts a new decision level. Once you've made an assignment, you propagate. So you do as much Boolean propagation as you can. And that's going to construct the level K. And after you finished all the propagation, either you get a conflict. In that case, you need to backtrack. Or then you enter level K+1, you make a new decision and you keep going. So as I draw the picture here, you have in each level, you have one decision literal, everything else is propagated. And what the CDCL implementation requires you to do is to keep track of why was this, why are these literals propagated. So for every propagated literal, there is a clause that caused it to propagate. And that clause is the reason that for the assignment. So this clause is special. It's split into one part CJ and the literal LJ itself. And CJ is false in the assignment that precedes, that's below LJ on the stack here. So all these literal between 0 and the one before LJ make this clause CJ false, and this force LJ to be true. Okay, so this is the data structure essentially that's maintained inside the CDCL stat solver. And so let's see what happens when a clause is false. So here is an example of a clause that's false. Because we've organized the clause, the stack in levels, we can split the clause into two parts. The part that contains only literals of level K and everything else as level less than K. And because of the way the CDCL works, this level K size here will have at least two literals. So what we do from there is we try to eliminate literals of level K until we get only one. And we do this elimination by looking at the reason why these literals were propagated. So for example, here I've eliminated LJ. So the reason we know that the clause is false, we know that LJ is true, so we know that not LJ has to occur in the clause. So we have a clause of the form, the C on the left-hand side contains not LJ. The reason for the propagation of LJ must contain LJ, so it must be of the form CJ or LJ. And the rule here that construct the new clause C prime is Boolean resolution. It's essentially you take a clause that contains not LJ, a clause that contains LJ, and you compute the union of both and you remove LJ from the result. So that gives you a new clause C prime. In that clause C prime, LJ has been removed. And you can see that this C prime is implied. The clause C prime is implied by the two clauses above. So it is sound to create this new clause and it's possibly added to your original problem. And you can also see that C prime has to be false in the current assignment because of what we described before. So the clause C is false. So everything except everything in this clause has a false value. CJ is false because we know it was used to propagate LJ. So by simple reasoning, this means that C prime is false. So what this means, now we can treat C prime exactly the same as we treated our conflict clause. So we can keep doing this elimination process on C prime. So you have to do this carefully. So you have to do it in the right order, doing basically top down from the top of your stack. And if you do this, eventually you're going to eliminate all the literals of level K but one. So you'll end up with a clause that looks like this. It contains a bunch of literals less than K and only one literal of level K. And that's the learned clause. That's what CDCL computes. So once we have the learned clause, we can add it to our set of clauses. And we are going to backtrack to a level where all literals in the list P0, PM, Q1, QR are assigned. So you compute the highest assignment literal for all these literals, and you backtrack to that level. At that level, this clause contains all literals that are false, plus one literals ls that is unassigned. And at that point, you can do unit propagation. So essentially, the idea here is we compute a clause, we backtrack to the point where we can do unit propagation using this new clause. That's the idea of CDCL. And that's the reason why CDCL has been so good in practice. Okay, I hope this gives you some idea. There's much more going on here, but this is the basic idea of how this works. So here is a full examples of a simple run of CDCL. So I've picked a simple set of clauses on the left. We start with an empty assignment stack. We do propagation at the base level. So you see, for example, that not y is a clause, which means that we have to assign not y to false to force this clause to be true. Once we've assigned not y to true, we can do Boolean propagation with this clause x or y here. So now we propagate x. Okay, you see that to make x or y true, given that y is false, we have to make x true. And that's it for level 0. Now we have to make a decision. We start searching. We have to pick a variable and select a variable and branch. So in this example, let's assume we pick t and we decide to make t false. So our decision is not t. At this point, we do propagation. So as before. So for example, from this clause here, we have to propagate not z. So we see that x is false, x is true, t is false. So that forces z to be false to make this clause true. And at this point, we have reached a conflict. We can see that z or t, one of our other clause, is false. So we enter the conflict resolution part of the search. So as I said before, we just process the assignment stack from top to bottom. So we look at the assignment for not z. We do a resolution step with z or t and this clause here. What we get by resolution is not x or t. So is this clear that you do z or t and apply this? So we eliminate z from the clause and we compute not x or t, which is not x or t. So that's a first step of conflict resolution. And it turns out in this simple case, because it has to fit on one slide, that this is the learned clause. It satisfies the property we care about. It contains only one literal t that's assigned at level 1, and x is assigned at level 0, so that's good. So we add it. So this is our learned clause. We add it to the set of clause here. And then we backtrack. And here in this case, we have to backtrack to level 0 because x is assigned at level 0. So we backtrack here. So now as we discussed, we are forced by the learned clause to make a Boolean propagation. So we are forced to put t to true by this learned clause. That was the whole point of learning this clause, to do this propagation. And then we can keep doing propagation steps. So here now we have this clause to satisfy, and the only way is to make z true. And that's it. We are done. We have found an assignment that satisfies all the clauses. And we know we are done because there's no more variables and we haven't found a conflict. So that's how CDCL solver works in practice. So of course, real problems are much, much bigger than that. So it's very common to have problems with 10,000, 100,000 Boolean variables and same large number of clauses. Okay. So another way of looking at the problem is this pseudocode here that summarizes what I was just described. So that's how more or less a solver works, a SAT solver works. You start with setting a decision level to 0. You start with an empty assignment, And then you keep executing this loop here. You start by doing Boolean propagation. If at the end of Boolean propagation, you found a conflict, then either you're at the bottom level, in which case there's no possibility of resolving the conflict. So you said you know that the problem is unsat. Otherwise, you learn a clause, you add the clause to your set of clauses, and you backtrack using this learned clause. If at the end of, and then you go back to the loop. If at the end of Boolean propagation, you look at, and there is no conflict, you have to make a decision. So there are two cases. Either all the variables are assigned, and this means that you have found a solution. Otherwise, you pick a variable, and you pick a Boolean value for that variable, and then you start a new level. So that's the abstract way of looking at CDCL. To make it work in practice, there are many more things that I can't really go into details about. One thing that's very important is decision heuristic, which variable you have to pick and which Boolean value you want to pick. That makes a huge difference. And that's also one of the reasons why CDCL solvers like Minisat and previous and even the new generation are very good. Something that is important also is to do restarts periodically. So from time to time, instead of doing, decision, you just decide I'm going to start afresh. And as we discussed before, you need to delete learn clause to not run out of memory and make your solver fast. And then you have a lot of opportunities for formula simplifications, and people also do alternate between search and simplification. That's what most modern SAT solvers will do. So you do this loop, and from time to time, you get out of this loop and you simplify your formula. And that's it. That's how CDCL works. Is there any other questions on this? Is this clear enough?
I have an observation.
Yeah.
I found it very interesting that sometimes you have to break the rules and try something different. With BDDs, it's the same thing. So perhaps it's something intrinsic to the problem. So with BDDs, you keep trying to find the right variable order.
Yeah.
If you follow the rules too closely, you might get stuck into a non-optimal solution. So from time to time, you have to break the rules and change the variable orders.
Yeah.
So it seems to be a similar thing that if you just follow the rules, sometimes you don't get an optimal solution, and then sometimes you have to break them. I thought that was
Yeah, that's very true. And that's also part of decision heuristics. You don't want to be stuck by making a series of bad decisions. And from time to time, you just do random. From time to time, you go randomly, pick a random variable and a Boolean variable. That seems to be a very useful feature. And it stops you from being stuck in a bad part of the search space. And restart is a little bit similar, although restarts are kind of complicated to understand when you do CDCL.
Great.
Okay, so that was SAT. SAT was the Boolean part of our problem. Now let's look at a decision procedure for the simple theory we discussed. So as we mentioned before, what we are looking at is functions and equalities, function variables and equality. A basic rule of reasoning in this context is congruence. So congruence is one of the basic axioms of equality. I wrote it here. Basically says that if you have a function, if you give the same argument to a function, you'll get the same result. That's what it's saying here. And computing the consequence of this rule is basically the basic algorithmic approach to solving satisfiability problem in UF. So by definition, we are going to construct something called a congruence closure, which is an equivalence relation on the set of terms that occur in your formula. And what this equivalence relation satisfies is it includes all the original equality. So you start with a set of equality E. Your congruence closure is based on E and the set of terms. And the one constraint is to make sure that if some equalities in E, then T and U are equivalent in the congruence closure. And then the second constraint is that the congruence closure is actually closed under congruence. So which is what this rule says here. If you apply a function to equivalent terms, then the result should also be equivalent terms. And it's the other condition is it has to be the smallest relation that satisfies these two properties. So it's like an inductive definition. Okay, so it's relatively easy to see that this congruence closure satisfies some very nice property. One of them is every implication of your equality is contained in the congruence closure. What this means, if any model of E, everything that satisfies all the equalities in E will also satisfy all the equalities in the congruence closure. So that's pretty clear from the definition. And the opposite is also true. If there is an equality that is not in the congruence closure, then you can find a model of E. So a model that satisfies all the equalities of E, but does not satisfy that equality. Okay. So essentially, E is going to summarize all the consequences. The congruence closure summarizes all the consequences of your equalities, of your original equalities. Here is the algorithm for computing this. So, oh, sorry, the indentation is wrong, but anyway. So you start with a finite set of terms, a finite set of equalities between these terms, and the set of term T must be closed under the subterm relation. So every term that occurs in your set of equalities and every subterm of these terms must be in T. And the output is an equivalence relation, which is the same as a partition of your set of terms. So initially, at the beginning, you assume that all the terms are in a separate partition, separate equivalence class. So everybody is in its own unique class. And then we process the equality one by one. So we add, when we process the equality T equals U, we search whether the class of U and the class of T are different. If they are different, we merge their equivalence class. So we create a bigger equivalence class that contains both of them. And then we propagate by searching for congruence. So we search for terms that satisfy these constraints here. And if we find some, then if we found two terms T and U that satisfy this constraint, we are going to merge the class of C of T and U. Okay. So that's the rule here. My notation is wrong. It should be T prime and U prime. It's not the same as the T and U here. Sorry about that. Okay, let's look at a simple example to show how that works in practice. So if you look at, so I have a bunch of terms here I chose, and here are two equalities, x equals y and y equals g of y. So we start with an initial partition where all the terms are in different classes. And then we process the first equality. We process the equality x equals y, which means that we are going to merge the class of x and y. And I describe this by marking an edge between x and y here. Then we do a congruence. And in this case, you can see that because x and y are equal, g of x and g of y must also be equal. So we propagate. And that's it for this equality. Now we look at the second equality, y equals g of y. So y and g of y are not in the same class, so we merge them. And now we see that we have constructed this bigger class here that contains x, y, g of x. From this, we can see that g of x is going to be equal to y because they are in the same class. And by congruence, this means that f of g of x and z and f of yz have to be equal. So we also merge them in their own equivalence class. And that's it. That's how we construct a congruence closure. And there are a relatively efficient algorithm for doing this, n log n algorithm. And that's the core of SMT solver for UF, for dealing with uninterpreted functions. Okay, so now that we know how to compute congruence closure, how do we use it to check for equalities for to use it as a decision procedure. So the problem now is we have a list or a conjunction of equalities and inequalities, and we want to know whether they are satisfiable in UF. And so here is an example here. You can see the first one is unsatisfiable, and I will show in a minute why. But you can kind of guess by substitution. You can see that this equality implies that these two terms are equal, and the second one is satisfiable. And the procedure to do this is described here. Essentially, you take all the terms that show up in these equalities. You split the constraint into equalities and inequalities. You compute the congruence closure using only the equalities. And then at the end, you check whether the congruence closure is consistent with your set of these inequalities. So if there is an inequality in the set of constraints that is inconsistent with your congruence closure, then you know that the problem is unsat, otherwise it is satisfiable. Okay? So this follows from the properties we described before, the properties of the congruence closure. So let's see what happens on the first example here. We have one input equality and one inequality. So we are just going to process that one. F of x equals f of x. So we start by merging the class of these two terms, and then we do congruence closure. So you can see here, these terms are equal. If I apply f on both sides, I will obtain a new equality. So which will lead to closure, to merging these two terms. So we have implied another equality implied by congruence closure. And then we can do another, as we did before. This implies now that f of x is equal to f of x of f of x. And by congruence closure, this is going to tell us that the last two terms are equal. And from this, and that's the end of congruence closure. And from this, we see that these two terms are equal and they are so this inequality, this disequality cannot be satisfied. And so we know that the problem is unsat. So that's how you use congruence closure to check satisfiability of equalities and inequalities. Now let's look at how we are going to combine these two procedures. So we have a SAT solver, we have a decision procedure based on congruence closure. How do we combine both? So the first step in SMT is going to be splitting formula into a Boolean part and a theory part. So we start with a formula, something that may look like this. What we do is we are going to introduce atoms, Boolean variables that are going to represent all the atoms in our formula. So here we have the negation of f of x equals f of z, and the negation of f of y equals f of z, and then we have equality between x and y and z and x. So we introduce just Boolean variables to represent these predicates, these equalities. And then, so this gives us a purely Boolean part that's obtained by renaming these atoms with Boolean variables. And then the theory part is basically keeping track of the mapping between Boolean variables and their interpretation in the theory. So we know that B represents x equals y. We know that D represents f of x equals f of z. So in principle, so here we get lucky, the formula was in CNF, but in principle, you also have to turn the formula, the Boolean part, into CNF. Okay, so that's some kind of pre-processing that you have to do to separate between Boolean and theory. So now that we have done that, the basic idea of SMT solving is to use the SAT solver to solve the Boolean part, find the Boolean assignment that satisfies the Boolean part, and then check whether the corresponding conjunction of literals in the theory is satisfiable. So, for example, here we can pick this assignment, not E, not E, not A, C, and D. That makes these four clauses true. That gives us an interpretation, how to interpret, how to convert this into first into an UF constraint by just following the definition. So not D means f of x has to be different from z, not E means f of y has to be different from z, and so on. Now we have a purely Boolean, purely UF problem, and it's only a conjunction of literals, conjunction of atoms, and negation of atoms. So we can use our congruence closure algorithm. And in this case, it's going to say it's inconsistent. You can see clearly x is equal to z, f of x different from z. That doesn't work. So now we are going to give new information to the SAT solver. It's going to backtrack and try something else. So here is another assignment. Again, we convert it to an interpretation for the atoms, constraints on the atoms. And in this case, now this is a consistent assignment. So we know that the original formula we started from is satisfiable. Okay, so that's at some high level, the whole idea of SMT solving. You use the SAT solver to enumerate Boolean assignment. Once you get a Boolean assignment, you call the theory solver to check whether the corresponding constraints on your atoms are satisfiable or not. If they are not, you backtrack, and if they are, you keep going, or you found an assignment. Okay, so that's the high-level idea. To make it work, we need to figure out how to communicate information between the theory solver and the SAT solver that's going to cause the SAT solver to backtrack. So one of the basic ingredients, one of the new things we need when we have to make the SAT solver and the congruence closure algorithm cooperate is theory explanations. And the theory explanation is a way of converting unsatisfiability at the theory level into clauses that will be useful to the SAT solver. So more precisely, what happens, what we need the theory explanation when we get a list of, in our case, a list of equalities and inequalities in QF that are not consistent. So you have a set of constraints on your terms that involve only equalities and inequalities. This set of constraints is inconsistent. You want to compute a theory explanation. In general, a theory explanation is just any subset of L that's inconsistent on its own. So in the worst case, you can just pick L itself. But just picking L itself is usually not very good. What you want is a smaller explanation, the smallest possible explanation you can get. So once you get by property of QFUF, the explanation is actually a valid formula in QFUF because the negation of the negation of the explanation is inconsistent. So we can add the explanation. It's valid to add the explanation as a new derived theorem. You can think of it as a theorem that's true in your theory. And because of the way we construct it, it can be converted into a clause, and we can give it back to the SAT solver. So that's the idea. We have a set of constraints which involve equalities and inequalities. We compute a subset of these constraints that are inconsistent. By the way we construct it, we know it can be turned into a clause, and then we give the clause back to the SAT solver. So to see how it works on the previous example, we had this assignment, and then that get converted to this conjunction of constraints. And two of them are sufficient. So x equals z and f of z and f of x different from f of z is our theory explanation, is one theory explanation for this inconsistency. And then when we negate this, we get f of x equals f of z, or z different from x, which, by the way we keep track of atoms, can be converted into a pure Boolean clause. So we know that D represents this, and we know that not C represents this. So now we have learned a clause like we did in CDCL, but instead of learning the clause from Boolean reasoning, we have learned the clause from theory reasoning. So that's a basic idea of CDCL. Okay, so of course, computing theory explanations in many applications is not that simple. So here is an example. You have 6 constraints here. And you can see that depending on how you look at it, there are many different, so these are inconsistent, and there are many possible explanations. So for example, you can pick this as your explanation. You have 3 atoms, you turn it into a clause, and that's these 3 atoms are included in your list here. Here is another explanation. It's better, it's shorter. Shorter is usually a better explanation. And here is another one, which actually, so these 2 explanations are based on the same conflict. Some equalities between this imply that these 2 terms must be equal. But there is also another inconsistency between h of xy and h of yx, which must be true by the fact that x is equal to y. So you could get another short explanation by doing different analysis. Okay, so how do we compute these theory explanations? So the basic problem is, how do we explain whether that 2 terms are equivalent in the congruence closure? So essentially, that's the basic thing we have to do to generate theory explanation. So we have a set of equalities as before, and we compute this congruence closure. And given the fact that 2 terms are equivalent, which means that they are in the same equivalence class, we would like to compute a set of equalities in our original problem that imply this equality, this derived equality. So ideally, we would like the smallest possible explanation. So the small possible subset of E that imply T is equal to U. Unfortunately, that's known to be NP hard. So we try to do approximation, essentially. We try to compute an explanation that's not too bad. And the approach that most SMT solver is due to these 2 people here. And it's essentially adding some extra information to the congruence closure that explains why 2 terms were merged. So as we saw in the little diagrams I showed before, you can think of congruence closure as building a merge tree between terms. And we can put labels on the edges of the merge tree that are going to tell us, is this merged because of, where these two terms merge because of an equality, or where they merge because of a congruence step. With these labels, we can compute explanation for an equality by finding the path from T to U in this tree. And then we basically that gives us all the equalities that show up on this path. And then we can recursively explain these equalities if some of them involve congruence. So that's essentially the idea of this algorithm. So let's see how it works in practice. So here I put the same example as before, and I put the congruence closure here at the bottom. And I've computed the congruence closure from left to right. So I've performed x equals y, then y equals g of x. So these 2 guys are marked as input equalities. And then everything else here was derived by congruence. And you can see, but by the way I build this congruence, that this equality here is ignored because the fact that y is equal to g of x is already known at the time we process this equality. So by congruence, we know that g of y is equal to g of x from this equality, and we know that y is equal to g of y from this equality. So at the time we see this equality, it provides no new information, so we just ignore it. Now let's see how we would explain the conflict and explain why f of g of x and z is equal to f of y and z. So we just find the path between these 2 terms. In this case, there is only one edge, and it's marked as congruence. So what we have to do now is explain why z is equal to z. So that's easy, there's nothing to do. Then we need to explain why is y equals to g of x. And to find the explanation for the fact that y is equal to g of x, we look into the class of g of x and y, and they compute the path from g of x and y. So we look at this path here. One edge is an input equality, so we keep it around. The other edge is a congruence rule, so we have to explain why is x equal to y. And we do it, again, by looking at the path from x to y in the graph. In this case, there's only one input equality, and we are done. So the explanation we would compute in this case for this congruence will be x equal y and y equals g of y. So essentially, if we go back to the previous picture, we would get this first explanation here. And the reason we don't get the second one is because of the fact that we have ignored this extra equality here because it was redundant at the time we processed. So in some sense, there is a conflict between avoiding processing redundant information and getting a smaller, better explanation. So by ignoring this equality, we forces us to generate this as an explanation, and it's not as good as the second one. So that's the trade-off, and that's why it's complicated to compute the smallest explanation. So there are some tricks you can play that try to avoid some of these issues. But essentially, that's the algorithm for computing explanations. Okay, so now here is the SMT integration in CDCL as I described it so far. So essentially, we just do Boolean solving, and once we get a full assignment, we just check the theory part. So this is the same algorithm as before. We do Boolean propagation, check for Boolean conflict. When all the variables are assigned, we get a full assignment. We can convert it to theory. If the theory says this is satisfiable, we are good. If the theory says this is not a satisfiable, it will generate a theory explanation. The theory explanation is a clause, and we know it is false in the current theory. In the current, it's false by theory reasoning in the current assignment. So we can exactly treat it exactly the same as a regular conflict Boolean clause. So we can do resolution and backtracking to make it true. And when we have nothing else to do, we do as before. We pick a variable and we do a decision. So that would be the naive way of doing SMT solving. So you can see that this is like the laziest way possible. You wait until you get a full assignment before checking the theory part. So even already, you can see that there are a lot of options on how to do this. In particular, what do you do with this C here? C is essentially a clause that's valid in your original problem. So you can add it as in your clause database as a regular clause. Or you can just drop it after you've done Boolean conflict resolution, Boolean conflict analysis. So you have a lot of options here, and different SMT solvers do it in different ways. What my solver does is it looks at the size of the clause, and there is some heuristic based on the size of the clause. If it's small, it is kept around. If it's too big, it is dropped, and it's used only once, and which means that potentially you'll have to recompute the same explanation later. Okay, so I assume you can all see that there is an obvious improvement, which is instead of waiting until you get the full Boolean assignment, you check consistency in the theory incrementally. So this is this variant here. The only thing is I have switched these two conditions here. We check the theory after there is no Boolean propagation. And instead of waiting until all variables are assigned, all Boolean variables are assigned, but the principle is the same. So the advantage here is if there is a conflict in the theory, then you may be able to detect a lot earlier than if you wait until all Boolean variables are assigned. So that's the idea. Now let's look at something else. If you only have theory propagation, theory explanations, you already have an SMT solver. But you can do better. You can do things called like what I call theory propagation, which is similar to unit propagation, but implemented by the theory solver. So here is an example of a congruence rule here. And if you assume that the Boolean, we have mapped these atoms to these Boolean variables, A, B, and C. And if the Boolean solver had decided that A is true and B is true, then we could propagate that C has to be true. But that's not true by Boolean reasoning. It's true by theory reasoning. So the theory solver has to do it. And that's called theory propagation. It's propagating Boolean variables in the SAT solver by theory reasoning. And the way that you have to do this essentially is almost the same as doing theory propagation. So the theory solver has to detect that C true is implied. So it does some theory reasoning, figure out that f of x is equal to f of z is implied by A and B equals to true. And from that, it can detect that C is implied. And so that gets added into the SAT solver truth assignment. And we need, later on, we might need to find an explanation for this propagation. And the explanation will be generated lazily and will be a clause. And the way you generate explanation in congruence closure is exactly the same way as you generate theory conflict. Okay. So that's a new trick, but it's essentially the same basic ingredients that we've seen before. The theory solver does theory reasoning, detects that some things are implied rather than detecting that some things are in conflict. So this gives us a new variant, and I didn't put too much detail here, but essentially now you interleave Boolean and theory propagation before checking for Boolean conflicts. No, actually, it's not very correct. Sorry about that. You interleave Boolean and theory propagation, and you stop when you get a conflict, and so on. So even though we do theory propagation, we still have to check consistency of the set of atoms. It's the reason we have to do that is because theory propagation is usually too expensive. And as I will show in a few slides, it's usually incomplete. Even if you were spending a lot of time, you cannot do it completely, so you cannot propagate everything. And this also complicates a little bit the implementation. So you need to extend your SAT solver and implement explanation generation trick and various things like that, so that you can get explanation for facts that were propagated by the theory when they are needed, when the explanations are needed. Okay, so this is a second improvement to SMT, and most SMT solvers have some variants of that. So one problem with congruence closure is it's entirely based on equalities. So congruence closure is a tool for computing implied equalities that are derived from previous equalities. So here is an example here. So congruence closure, you see this axiom of congruence, x equals y and y equals z implies f of x equals f of z. So that's true by congruence and equality reasoning. And if you assume that these atoms are mapped to variables a, b, and c, the congruence closure will be able to propagate that a and b implies c, that is reasoning in the forward direction here, x equals z and y equals z implies f of x equals f of z. But it will not be able to generate theory propagation if c is false and a is true. Even though, so logically, if c is false and a is true, we know that b has to be false. Essentially, what was he saying is f of x is false, f of x is different from f of z, x is equal to y, so y must be different from z. So that's also true by theory reasoning. But the congruence closure algorithm cannot compute that because it only looks at equalities. So this is a limitation of congruence closure, which means that it cannot be as efficient as we would like in terms of theory propagation. So what we can do in this case is something a little bit different, which is in this case called dynamic Ackermannization, which is compiling Boolean theory reasoning into new clauses. So adding new clauses on the fly that represent that encode some facts that are true in the theory level. So in this particular case, Ackermanization is the idea of replacing equality between terms but by Boolean atoms. And it's applied heuristically in the CDCL-T framework, because if you do this brute force, then you are going to generate so many terms that you are going to die and run out of memory. So how does it work? You start with, say, a congruence rule like that. And how do you encode this in Boolean as a clause? Essentially, you need to create Boolean variable for all these equalities. So if the Boolean variables are already around, then that's good. You don't need to create anything. Otherwise, you need to create dynamically new atoms and new Boolean variables. And then you create, and then you can just convert this into a clause. So if I have A to represent X equals Y, B to represent Y equals Z, I may need a C to represent this new equality. Once I have the C, I can convert this into a Boolean clause here, not A or not B or C. Okay, so that's another trick that you have to do in many cases in SMT solving, is convert theory reasoning, theorems that are true in the theory, into clauses and give this clause to CDCL. Again, that leads to some complication because now we are creating dynamically new terms and new variables in the SAT solver. And we're also adding dynamically new clauses. So you have to do all sorts of bookkeeping and all sorts of implementation tricks to maintain your data structures in a good state. Okay, so that's, I don't know how much time I have left. That's most of what I wanted to say about SMT.
Well,
so
not much time, we ran out of time, but please continue.
sorry. So this is the summary, if I can do it quickly, is basically what I said. CDCL modulo T combines a CDCL SAT solver with a theory solver. The communication between the two is the SAT solver produces Boolean assignment and the theory solver produces clauses that go back into the SAT solver. You need to support explanations for conflicts that, as a minimum. It's good to also be able to do propagation, and it's also good to be able to create lemmas dynamically. And if you want to know, let me skip that. And if you want to know about SMT in general, there are many more things to say. I just described the very basics. There are many more theories. You also need to be able to combine theories. You need to be able to handle quantifiers. And there are even other techniques than CDCL-T that I will not describe today. So if you're interested, I can give you reference, or you can just Google or go to search the literature for work on SMT. There's a lot of work in these different areas. Okay, so I'm going to conclude here. Thank you for the attention. Do we have more time for questions? Or?
Well, a few questions. Yeah, thank you, Bruno. It was a very, very interesting talk. It's a fascinating topic, and you know, it's always interesting to learn new things about it. We have time for a few questions. If people have questions, they can ask in the microphone, or they can type in the chat if they want.
I have some question, very quick. Thank you so much, Bruno, for opening the box for us about the SAT and SMT, at least to know what usually standard and what you also, the gaps where each tool kind of fill up and have the different performances. And it's more a generic question about your experience in using SMT and SAT in Amazon. Could you talk a little bit about your experience there, the usage, just to illustrate, because there may be some students here as well, and to know the application of these techniques as well?
Yeah. So at Amazon, one of the main use of SMT solvers is in verification of security policies. So AWS provides different resources and different services. And the users, they may have some constraints on who can use and who is allowed to execute some services. So for example, you can say, okay, I'm going to create some kind of internal server. I want to make sure it's not accessible from the internet. So you can encode these rules into a policy language, a security policy language that Amazon has developed. And we provide tools that people can use to check whether their policy means what they want. So for example, as I said, you can write a policy and then you can ask, is it possible from any random person on the internet to access my server? And by analyzing that policy, you can figure out whether the answer is true, yes or no. And the way it works is by converting the policy language into SMT. And in this case, it's a combination of constraint on strings and arithmetic. So that's one of the biggest applications. So you need SMT solver that can handle string constraint, regular expressions and string constraints. So that's one of the biggest applications of SMT solvers. The way they implement it is by using portfolios. That's also something very interesting, that because the theory of strings and regular expression is quite complicated, we don't get good performance by just using one solver. We have to use several solvers in parallel and give them the same input, and we get the answer from the fastest one. Otherwise, it doesn't really work. Other applications are more related to software development. So I don't know if people know of Daphne. Daphne is a tool for writing software that includes theorem proving. And the way you write software in Daphne is you can write pre and post condition for your methods, invariants for your loops, and these all get converted, and then Daphne will make sure that all these invariants are satisfied. And the way it does it is by doing SMT solving, converting to SMT solving, and using Z3 as an SMT solver to check these problems. That's another big class of applications. For SAT solving, we have different applications for SAT solving. Again, one of the biggest one is bounded model checking of software. So some part of Amazon, they develop very critical software, and they want to check that there are no bugs of a certain kind, like memory violation and things like that. And they use a tool called CBMC, which is a bounded model checker for C. And at the back end of CBMC, we have different SAT solvers. Again, it's a software engineering application, software development application. I think that's the main application I can talk about. There are others that are not public, so I probably cannot.
Okay, yeah. No, but that's enough. Thanks a lot.
Yeah,
Sure.
thank you. Lucas beat me to it. I was going to ask you, and that's a fascinating, again, overview of the things that this can be used for. So
Yeah.
that's very, very interesting. So any more questions? So let's thank our speaker.
Thank you.
Yeah, and we should be back at 3 p.m., right, Lucas?
Right, yeah, we have some time now, and hopefully with good news from the World Cup, right?
Oh, that depends if there are any Croatians in the audience.
Oh, okay. Thank you so much, Bruno.
Thank
Thank
you.
you, Bruno.
Thank you. Bye-bye.
Bye-bye.
Bye-bye.